In this video, we're going to look at the chi-squared distribution. CHI is pronounced chi. And what does it do? Well, it tells us two things, the ones that we are going to use anyways, is it tells us whether or not the distribution that we are looking at matches some other known distribution. And it also tells us whether or not two things or more than two things are independent. So actually the chi-square could look at what we did in chapter 10 when we had that matched pairs, and it should confirm or deny that they were actually truly matched pairs. So that's kind of an interesting little side gig, which by the way, I did run our last example in 10.4 into the chi-squared, and it did actually say, yeah, they are actually dependent. So that was kind of nice to confirm that we expected them to be matched pairs. So on a side note, so what the chi-square distribution gives us is it tells us whether or not that a distribution that we are interested in matches a known distribution, and also whether or not the two things or many things that we are looking at are independent. Now, the one that we did in chapter 10, it made sense that they weren't independent, but what happens if we have more than two things that we are looking at? So obviously a matched pairs are dependent. There's going to be other times in which we're going to get information and we won't know whether or not they're independent or not, and so the chi-square will give us that information. A couple of things that have to happen with the chi-squared is that the degrees of freedom depends on how many chi-squareds is being used. For the chi-squared distribution, the population mean is mu, and it equals the degrees of freedom, and the population standard deviation is 2 times the degrees of freedom and the square root of that. The random variable is a capital X or a lowercase x squared. The random variable for a chi-squared distribution with k degrees of freedom is the sum of the k independents squared and the standard normal variables, which look something like this. And we're mostly going to be having the spreadsheet do all this stuff for us. The curve is non-symmetrical and skewed to the right. There is a different chi-squared for each degree of freedom, so that makes life that much more fun. Just be grateful we get to use Excel spreadsheets and we don't have to look this stuff up in tables like we used to have to back in the old days. The test statistic for any test is always greater than or equal to 0, so that's good to know. So we won't have to worry about taking the opposite of it if it ends up being negative, because it won't be negative. The degrees of freedom are greater than 90. The chi-squared approximates the normal distribution. The mean mu is located always just to the right of the peak. So here's some examples. So we're going to look at the expected values. So we're trying to decide whether or not the information given to us matches what we expect it to be. So this is the chi-squared where we are taking and looking to see whether or not the information matches the distribution of what we expect. At Centralia College, 80% of the students are from Lewis County, 14% are from Thurston County, 4% are from Grays Harbor, and 2% are from elsewhere. If we randomly selected a survey of 500 Centralia College students, what are the expected values for the residences of this sample? So of course, the expected value is we have 80%, so 80% equates to 0.8 multiplied by the number of students. So we would expect 400 to be from Lewis County. Now 14%, so 14%, which is 0.14 multiplied by that 500. So we would expect 70 from Thurston County. If we have 4%, so that then becomes 0.04 multiplied by that 500. So we would expect 20 of those 500 students to be from Grays Harbor. And then 2% equates to 0.02 multiplied by the 500, which is going to be equal to 10 students from elsewhere. Now this is not the chi-squared. This is just saying this is what we expect. And then we can actually do the chi-squared to see whether or not what we have matches up to what was expected. Here's another example. A certain event should not be dependent on the day of the week. If we check on 200 observations of this event, how many should be on each day? So because of the fact that we expect them to be the same each day, because it shouldn't be dependent on the day of the week, this should be a uniform distribution. So since there are 7 days of the week, we would take our 200 and we divide by 7, and this would be what we would expect to find. We will not round, so do not round, and we would expect this to be a normal distribution. Now, we have to do the expected values before we talk about the chi-squared. So here's my expected values in these two examples. The three major applications of the chi-squared is to see if the data fits the particular distribution, which we talked about. Test if they're independent, which we'll do, and the test of single variance. We won't do that in this class. Single variance, the test of single variance is not at this level of statistics. That would be at a higher level of statistics. So we're not going to worry about that. What we're going to do then is to look at the goodness of fit. So the goodness of fit would be like the Lewis County example where we had the Centralia College students, and we would then decide whether or not the information we are getting is following what we would expect. So this hypothesis is the one that gets expressed as a sentence, or it could be a mathematical statement. Now, up until now, we usually use mathematical statements, but now we can actually write this as sentences, and sometimes it makes more sense to write it as sentences. The test statistic actually is really quite straightforward. It is going to be the observed minus the expected, that quantity squared, divided by the expected for each and every data piece, and then we're going to sum those up. So that's kind of nice. Now, there should be n terms, so the degrees of freedom would be the number of categories minus 1, so just like we expect in Chapter 9. The goodness of fit is almost always right-tailed if the observed values or corresponding expected values are not close enough to each other. Then the test statistic can get very large and will be way to the right of the tail of the chi-squared curve. P-values. P-values require a new distribution. It's actually built in to our Excel spreadsheets, and it is going to be the equals, the chi sq.distribution.right tail. We're going to grab our calculated test statistic, comma, and then our degrees of freedom. Now again, remember the degrees of freedom is the number of categories minus 1. So if we go back to our example, which was, so we have the 80% is from Lewis County, 14 is from Thurston County, 4% from Grays Harbor, and 2% are from elsewhere. We surveyed 500 students, and this is what we actually got. We got 429 from Lewis County, 40 from Thurston County, 25 from Grays Harbor, and 6 from elsewhere. Now, if you remember, the numbers we got was 400 from Lewis County, the expected, 70 from Thurston County, 20 from Grays Harbor, and 10 from elsewhere. So what is the hypothesis on this? And my hypothesis, my ha, I'm actually going to write in words. And my ho is the two distributions are the same. What does that mean? Well, that means that even though my numbers don't match up to the expected, I expect that we can consider them the same, that the information that we had from Centralia College is still holding true. And the ha would be, they're not the same. Distribution. Stribution. Okay, the test statistic. Well, so for my test statistic, I would go out and I would put in first, and I'm going to show you on a spreadsheet, I would take the observed, I would take the expected, and then I would find that difference. So I would need to enter my observed, I need to do my expected. I might put a difference, or I might just say, hey, I know that to find my test statistic, it's going to be my observed minus my expected, the quantity squared, divided by my expected. So I might build something that looks like that, enter my observed, my expected. In this, I would do an equals, and then I would have this and pull it through. What I got for my test statistic when I did this, and I'll show you my spreadsheet here in a minute, is 17.8096. Now the p-value, because my test statistic is that, I'm going to go in and I'm going to do the equals, the chi-CHISQ dot dist dot right-tailed. My degrees of freedom, so my degrees of freedom is going to be the number -1, and I had 4 minus 1, so this is 3. So I would have used the chi-squared to get my p-value, and I end up with a p-value of 0.00048. So what is the decision? At a 5% level of significance from the sample data, there is not sufficient evidence to conclude that our student breakdown actually matches the given student breakdown. So we are going to reject the HO. We're going to say that there is not evidence to support the claim. There is sufficient evidence to conclude that the breakdowns are different. Okay, so then again, here is the one where we had those numbers of people that came in during the week, and our HO is that there's an equal distribution across the days of the week. HO is equal distribution across the days of the week. And the HA is, of course, that they are not equal. So I again would do my observed and expected. Now, when I did this, I got my test statistic, by the way, to be 9.09. My p-value, since I have 7 pieces of data, because there are 7 days a week, my degrees of freedom is 7 minus 1, which is 6. And so my p-value is 0.169. Now my decision is that at a 5% level of significance, the sample data, there is sufficient evidence to conclude that a certain event that we were looking at has an equal distribution across the entire week. So to do all of this, we're going to need a spreadsheet, and this is the goodness of fit spreadsheet. Now I have the observed, I have the expected, and in this cell, what I did was I did an equals. I grabbed the cell that had the observed, I subtracted off the cell that had the expected, had parentheses around it, and then I squared it, so raised it to a power of 2, and then I divided by the expected. Now I entered all of that here, and then what I did was I just pulled that corner down and pulled it all the way down to the bottom. So even if those other cells were empty, it should be calculating it. And then of course, this is the sum. And because it is the sum, I need to have a capital SUM because I am asking Excel to make that sum for me. So that should be a capital SUM, and then I'm just going to grab the column above. My degrees of freedom, and this is what I did a count A. And so a count A, and then I grab the cells with the last column with entries. And so I'm going to grab this entire column, and it's going to count. And it's only going to count if it's not empty, and I got 4. That means my degrees of freedom is 3. And then I use the chi-squared dot dist dot right tail. I grabbed the cell that had the test statistic. I grabbed the cell that had the degrees of freedom. I entered my alpha, and then down here you can see I made the decision about to reject or fail to reject. So this tells me whether or not two things are matching in terms of distribution. We could use this if we believe something is a normal distribution. We can check it against what we would expect for a normal distribution. Test for independence is the second chi-squared that we do in this class. And again, this is to determine if the information that is given to us is independent of each other. Now, I said that I actually did this with our last example in chapter 10, and it proved that they were not independent. So we will again need to have the observed minus the expected, and it's going to be squared and then divided by the expected, and then we add this all up. Now, the thing is that we're going to do it by rows and columns, and we're going to need to build a table, and this is going to be a lot of fun. The degrees of freedom will be the number of rows times the number of columns, and it will be in the terms of this. The test for independence is always right-tailed because a calculation of the test statistic. If the expected and the observed values are not close together, then the test statistic is very large and way out to the right of the chi-squared curve, like the goodness of fit. In a test of independence, we will state the null and alternative hypothesis in words. There won't be any symbols. Since the contingency table consists of two factors, the null hypothesis states that the factors are independent, and the alternative by default is always they are not dependent. So if we think about what happened in chapter 2, if A and B were independent, then if A and B both happen, it was the probabilities of each one of them happening individually, and we didn't have to worry, and as a multiplication. We didn't have to worry about subtracting off any overlap. We weren't adding stuff. This is what we did. So the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. Our null and alternative hypotheses are always the same on these. Either they're independent or they are not dependent. If we reject how the variables are dependent, if we fail to reject, the variables are independent. You should verify the values are expected and the values are 5 or bigger, that the population size is at least larger than or equal to 20, and it's safe to say that the population size must be greater than or equal to 20 times the number of pieces of data. Okay. So college students may be interested in whether or not their majors have any effect on their starting salaries after graduation. Suppose 300 recent graduates are surveyed as their majors in college and their starting salaries after graduation. The tables are shown below. Here's the major. 5 people after graduation was less than 50,000. 20 people were between 50 and 68,000, and 5 were more than 69,000. Engineering, nursing, business, and psychology. So we have 3 things going on here. So my alternative and the null hypothesis, they're always the same. The hoe is always going to be the same, and it's going to be the starting salaries and the majors are independent. So salaries, starting salaries, and majors are independent. And the hoe would be that they're not, or excuse me, the ha would be that they are not. Okay, we're going to have a spreadsheet that does this. But if I look at my degrees of freedom, my degrees of freedom are the number of rows, which I have 1, 2, 3, 4, 5 rows. My degrees of freedom is the number of rows, which is 5 minus 1, and then it's going to be multiplied by the number of columns minus 1. So I have 3 columns. So again, we're going to have our spreadsheet calculate this. So this is 3 minus 1, and so we have 4 multiplied by 2, which is 8. Test statistic. I actually get to be, and I'll show you my spreadsheet, 33.54455. My p-value, I got to be basically 0. So what does it say? Well, we are going to reject the hoe. Why? Because my p-value is approximately 0. So that tells us the majors and starting salaries are not independent events, and that kind of makes sense, right? Nursing students, when they graduate, typically will make more than an English major. Engineering students will make more than a nursing, so that is not uncommon. So here's the spreadsheet. Okay, now what I didn't put here is what I did is I did the sum, I did an equals, I did the sum, and then I grabbed all of these. So I did the sum and then I grabbed that entire row. And I did the same thing here, 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 and here, and here. Similarly, in this here, I did the equals and I typed in sum, and then I grabbed everything that was above it, and I did the same thing across this entire this entire row here. And then here I summed either this way or this way, it doesn't matter. So this part is the easy bit. Now, the expected values table, this is way more interesting. So this is what we do with the expected values table, is each and every one of these, we're going to have, in each and every one of these cells, we're going to have an equals. We're going to grab row A. So we're going to grab the entire row A from up here. Okay, so I'm going to come up here and I'm going to say, what I did was I did if. So in Excel, I did the equal sign and then I typed in if. I did a parenthesis. And then I grabbed this entire row, not including the totals, but this entire row from this entry to this entry. And then I said equals 0, comma, quotation mark, space, quotation mark, comma. And then I grab the row total, which is this entry here. I multiplied by the column total, which is this entry here. And then I divided by the total, which is this entry here. Now, for this entry, I did the same thing, except for now the column total is the second column. Still the second column. This one would be exactly the same as the very first one, except for now the column total is the third one I'm grabbing. Now, similarly, I'm going to go down here and if row B is equal to 0. So again, I type in equals F and then I do a parentheses. I grab this entire row from the 10 all the way down to here, but not the total. And I write equals 0, comma, quotation, space, quotation, comma. I'm going to grab my row total, which is 100. I'm going to divide or multiply by my column total, which my first entry would be 55. And then I would divide by this entry here, this cell. That would give me the 18.33. This one, again, is going to be the exact same thing. I'm still going to grab a row B. I'm going to grab my row total, which is the same. Now my column total has moved over one to this, and my total is still this cell here. So that's how I do the expected values. To do the test statistic is I'm going to do if expected row and column, that's this. So this is in position 1, so row 1, column 1. So if this, that's this expected row and column, so that's saying if this cell is equal to, and then I did a quotation comma, or quotation space, comma, and then quotation space, comma. So this is saying, hey, if this is empty, this is what I want you to do. I want you to grab the given row and column. Well, the given row and column is this entry right up here. So when I'm talking about this entry, so this is the entry, that's the cell I'm going to grab. That's my given row or column. I'm then going to subtract off, and I'm going to grab this cell there. And then it's going to be, have a parentheses, I'm going to square it, and then it says divide by the expected. Well, then I'm going to go again and I'm going to grab this cell right here. Okay, so that's how I'm going to fill out that entire set here. So this one again this is the second column, this first row. The expected row and column is this number. So I'd grab this cell and say, hey, if this thing is not equal to 0, then this is what I want you to do. If it is equal to 0, then you do nothing. So that's what this says, expected row and column. So I would, for this one, because I am going to grab this cell, I'm going to say, hey, if it's not empty, then I want you to take the given, which is up above, subtract off this one, square it, and then divide by, of course, my expected. So you can see that I have my expected, I have my test statistic. Then, now this is where I'm going to do my degrees of freedom. So my rows, so I do a count and I do row, and I grab row A dot row F. So I'm going to grab whichever row A is and row F is. Or I can put these in if I want by hand. You know, it's not a big deal to put in by hand. And then my test statistic is going to be the sum of the test statistic table. So what I'll do is I will do an equals here, and then I will sum, and I'll type in the word sum, and then I will highlight this entire thing, And so it's going to give me my entire test statistic, and that's where I got that 33 from. Now, my p-value is going to be the chi-squared dist dot right tail. I grab this cell, and then I'm going to have my degrees of freedom. And my degrees of freedom, I can add an extra row in here if I want and do df. In my degrees of freedom, I would grab this -1 and this -1 and multiply the two, which is where my degrees of freedom come from. And that's it. Now, this is one that if you need help for in class, we will spend some time in class to do, because the handout for chapter 10 and 11 isn't that long in and of itself. So I suspect that next week we're going to have some extra time toward the end of the week to build spreadsheets, look at any kind of, what is it we want, what are we doing, labs, or anything like that in class. And we'll see you in class, and we'll see you online. Let me know if you have questions.